Welcome, fellow chemists, to a video about how to determine the molar mass of a substance. This is one of the simplest calculations you will learn to do in chemistry, so it's really nice that chemists have a competing term for this value, formula mass. There is a distinction between molar mass and formula mass from a definition and application perspective. However, if you are in a first-year chemistry course, they are basically indistinguishable. When you calculate molar mass, you are essentially finding the formula mass, but you are calling it the molar mass. Now, before I explain what on earth I mean by that, let me make an adjustment to the periodic table to make things as simple as possible. As you know, the table is filled with decimals, which can make things unclear, so I'm going to take the atomic masses of all the elements and round them to the nearest acceptable whole number. I will use this rounded periodic table for all the calculations to come. There are links in the description for you to reference this or to print out your own. With that done, let me explain what I said a moment ago. By definition, molar mass is the mass of 1 mole of a substance. So let's say I gave you 1 mole of a simple substance like table salt. Can you determine its molar mass? If you have no idea what to do, does giving you the chemical formula help? Now that you have the formula of table salt, you could probably figure it out, even though the definition I provided a few seconds ago is remarkably unhelpful. Something remarkably helpful is a simple table. It may be unnecessary for something as small as NaCl, but you'll see how useful it is with larger formulas and, whenever I get to it, percent composition. The two elements in the formula are sodium and chlorine, and as there are no subscripts indicating otherwise, there is 1 atom of each. According to the rounded periodic table, sodium has a mass of 23 and chlorine has a mass of 35. The total mass of sodium present is 1 atom times 23, and for chlorine it is 1 atom times 35. Take those contributions, add them together, and the total is 58. But is 58 the molar mass? If the unit is AMU, then we technically have calculated formula mass. But if we give it the correct unit, grams per mole, we can now call it the molar mass. And at this level of chemistry, that is more than good enough. So if we are not at a level where we really need to worry about nuance, then I propose a functional definition which better describes what we often do to find it. Definitions aside, the sodium chloride example should have demonstrated how simple the calculation is, but beware the chemical formulas you might be working with can be more complex. Water is a nice simple formula with a subscript in the middle, but there are others that have parentheses in them or dots in the middle which aren't used to multiply, and even some with brackets. Feel free to skip ahead to the chapter that has the example formula you need additional help with, but I've got one last simple formula. Can you determine the molar mass of lithium fulminate? I'm sure you had no problem with this one because the elements are easy to identify and there is only 1 atom of each. After finding their atomic masses and doing a bit of multiplication and addition, you surely arrived at the correct value of 49 grams per mole. When the formula only contains symbols, it's a piece of cake, but most formulas like that of water will contain subscripts. These numbers indicate exactly how many atoms of a particular element are present, kind of how coefficients are used in mathematics. In the formula H2O, the 2 is sandwiched between hydrogen and oxygen, so which element does it go with? Unlike in math where the coefficient is in front of the variable, the subscript is actually behind the element it goes with. While the positioning may take a bit getting used to, they are similar to coefficients of variables in algebra in that they are multiplicative. Of course, this means that there are 2 hydrogens in water. Oxygen doesn't have a subscript, but we have already applied the convention that simply writing the symbol means it is there once. Finding the molar mass of water is simple from here. There are 2 atoms of hydrogen, each with a mass of 1, and oxygen has a mass of 16. Multiply across and add the totals, and the molar mass of water is 18 grams per mole. When a formula is a bit longer, like it is for riboflavin, you just need a larger table. Can you determine the molar mass? There is no guessing or remembering conventions to get atom counts for each of these elements. As you get familiar with the periodic table, you'll memorize these atomic masses pretty easily too. After that, a bit of multiplication and addition later, and the molar mass is 376 grams per mole. Now for the final practice in this chapter, what is the molar mass of vitamin B12? I did not add this one because I thought calculating the molar mass would trouble you. Instead, I need to point out something about the answer we get from this calculation, 1,354 grams per mole. A molecule with this many atoms actually demonstrates the limitations of my rounded periodic table. If we use the proper atomic masses, the molar mass is a bit over 1355. My rounding is sacrificing the accuracy of the answers, but I'm trying to show you a method which, as you can see on the screen now, can easily accommodate actual atomic masses. While vitamin B12 has a large formula, it is easy to determine how many atoms of each element are present. What about this one though? Using what we know, the 3 directly next to the oxygen is telling us exactly how many atoms there are. The 2 outside of the parentheses is not telling us how many atoms there are, but exactly how many groups of NO3 there are. Ignoring the 2 initially, the atom counts are very straightforward. The 2 is multiplicative, but it only distributes inside the parentheses, so nitrogen and oxygen will each double, and magnesium is unaffected. Finding the molar mass from here is really easy, and it comes out to 148 grams per mole. A good source for ridiculous formulas is a list of minerals, so here is that of Brazilianite. Don't be afraid of the 2 sets of parentheses, you've got this. The 2 sets of parentheses means we are going to distribute twice. What we need to be aware of is oxygen shows up in 2 places. But if we take our time, it really is not that difficult, as the initial counts are more straightforward than it may appear. Sodium and aluminum are easy. Phosphorus is inside parentheses, but it has no subscript of its own. The first oxygen has a 4, the second no subscript, and the hydrogen none as well. I've kept the first and second oxygen counts separate for now, and you're about to see why. Distributing into the first set of parentheses, phosphorus and the first oxygen double to 2 and 8 respectively. When we do the same into the second set of parentheses, the second oxygen and hydrogen both quadruple. Now that all subscripts have been accounted for, it makes sense to combine the oxygen counts to one value. From here, you know everything that remains in order to find the molar mass. And after completing the multiplication and addition steps, the result is 362 grams per mole. Adding parentheses really didn't up the difficulty level too much. For first-year students, the most complicated looking formula is probably like this. This is the formula for copper 2 sulfate pentahydrate, and a common lab involving hydrates such as this is to determine the ratio of water molecules. As you can see, the value is 5, but that dot in the middle does not mean we multiply by it. Instead, use the dot to separate the formula into left and right sides. On the left side, the elements and counts are very easy. On the right, the initial count is easy too, but what to do with the 5? As the name stated, this is a pentahydrate, which means there are 5 water molecules present. While the subscript 2 in water only goes to hydrogen, the 5 in front refers to the entire thing, and so the initial counts of water alone are multiplied by 5. From here, it's just a matter of finding atomic mass, doing a bit of multiplication and addition, and the molar mass is calculated to be 250 grams per mole. Not every chemical formula with a dot in the middle of it will be a hydrate though. This substance, sodium percarbonate, is known as an adduct, but I know you can figure out its molar mass. The only difference this time is that there is a number on both sides of the formula. On the left is sodium carbonate, and the initial count is easy to find, but of course that 2 in front means all of those values must be doubled. On the right is hydrogen peroxide, and its initial count is easy too, but must be tripled. You know what's needed next, and after a bit of multiplication and addition, we calculate a molar mass of 314 grams per mole. If you're just beginning your chemistry adventure, with the exception of the hydrates, you probably don't have to worry too much about seeing dots in your formula. If you think you may go a bit further into the field, and especially into the chemistry of complexes and minerals, there's a good chance you encounter brackets like this. You're looking at the formula of the mineral henmelite. I've ditched the 1 mole on the screen because not only has it been unnecessary, this formula is quite big. There's a lot to unpack here, but nothing truly new. You know by now the subscript on a symbol is exactly how many atoms there are, and a subscript on parentheses is how many groups of atoms are present. When there is a subscript on brackets, it is exactly how many groups of groups there are. The subscripts are still multiplicative, so when you see brackets, you'll just need to be a bit more careful with your calculation. You may prefer going through the calculation differently than I'm about to show, but before I do it, why not give it a try yourself? The elements in henmelite are easy to identify, and oxygen and hydrogen are in 2 different places. The initial count is easier than it looks because outside of brackets and parentheses, only calcium has its own subscript. Inside of them, boron only shows up once and has no subscript, and each time oxygen and hydrogen show up, it's only a 1. Now we can work inside of the brackets and out. We already have the 1 boron atom, and the 4 distributes to the OH group. Next, it is time to distribute the 2 inside the brackets, and it will double the amount of boron, oxygen, and hydrogen. The oxygen and hydrogen inside the parentheses at the end of the formula get quadrupled. Since all subscripts have been accounted for, we can find the totals of oxygen and hydrogen respectively. Once we reach this stage, all molar mass calculations are exactly the same. Get the atomic masses off the periodic table, multiply those values by counts to get a total, then add everything. Although the formula is ridiculous, the molar mass of 370 grams per mole was not that difficult to calculate. So there's really just one thing left to do. Put all of the concepts in the previous chapters together into one ludicrous formula. There are plenty of symbols, but only 6 unique elements in this formula. Arsenic shows up twice, oxygen 6 times, and hydrogen 3. You might be wondering why I don't have oxygen and hydrogen twice in the table, despite the formula being a hydrate, but as you can see, the screen is quite crowded, and adding 2 more rows would only make it worse. The color coding should be helpful in distinguishing the atoms. Counting the atoms starts off easy with sodium and aluminum. Arsenic shows up twice, but neither have a subscript. Oxygen is here 6 times, where the first, third, and fifth have subscripts, but the second, fourth, and sixth do not. Hydrogen is found 3 times, and only the one in water has a subscript. Finally, subscriptless sulfur appears only once. To update the counts, I'm going to go left to right starting inside brackets and working my way out. Inside of the first set of brackets is already done. A 4 gets distributed inside, quadrupling the first arsenic, first and second oxygen, and first hydrogen. Inside the next brackets is a set of parentheses into which a 2 is distributed to the fourth oxygen and second hydrogen. Then the 2 outside of the brackets will double the second arsenic, the third and fourth oxygen, and second hydrogen. It's much easier now as the 2 outside of the last set of parentheses doubles the lone sulfur and the fifth oxygen. The last thing to do is move to the right side of the formula and quadruple the third hydrogen and sixth oxygen. With the initial counts for each separate occurrence of all the elements completed, arsenic, oxygen, and hydrogen can be combined into their respective totals. It has taken a bit of doing, but by the time you're done finding the atomic masses, multiplying across, and adding the totals, that monstrosity of a formula turns out to have a molar mass of 1,302 grams per mole. If you use actual atomic masses, the value is slightly smaller. Whether the formula is simple or ridiculous, there are always 4 steps to calculating a molar mass. First, you must carefully count the number of atoms. Then you must refer to the periodic table to find each average atomic mass you need. Next, multiply the number of atoms by the atomic mass to find the total an element contributes. Finally, you will add together all the totals to get the molar mass itself. This video, along with those on balancing equations, is actually a prerequisite to my 4-part stoichiometry series, which will already be in the queue by the time this video goes live. Feel free to leave comments and requests below, and until the next video is posted, thank you very much for watching.